Hello and welcome back. Today we are talking about continuity. We're going to answer a number of questions, the first of which is, well, what is continuity? How do we determine if a graph is continuous? What do limits have to do with continuity? And finally, what is the intermediate value theorem? First of all, what is continuity? We're talking about graphs here. So a graph is continuous if it has no interruptions, if it's unbroken, or it has no holes, jumps, or gaps, like that pretty little thing there. It's just a very smooth graph. But what is continuity mathematically speaking? A function f is continuous at c on the closed interval ab if all of the following are true. Number 1, the function is defined at c. Number 2, the limit exists at c. And number 3, the two-sided limit is equal to the function at c. So let me show you what that looks like. Okay, number 1, is the function defined at c? So we'll call this little spot here c. And is the function defined there? Yeah, right there. So number 1 is taken care of. Does the limit exist at x equals c? So at x equals c, are the left-hand limits and the right-hand limits headed towards the same spot? Yes, they are. Number 2 is taken care of. Number 3, is the two-sided limit equal to the function at c? Well, no. Like the graph is headed way up here at the top, right? But it never gets there. It heads down here. So no, we cannot check off number 3. In order to check off number 3, what would happen is where the function is defined, that would have to agree with the limit. That dot would just have to move up to the top, and boom, now we have a continuous graph. Not all graphs are continuous. So I'll show you some unexamples. And you can see by just looking at the graph that they're not continuous. But let's also look below the graph at why mathematically they're not continuous. So for A, well, in the middle, it just kind of whoop goes off into infinity. The limit at f of A doesn't exist. Actually, f of A doesn't exist either. So not continuous at all. B, the limit doesn't exist at A. The graph is it's going to a different spot. The graph itself exists at A, but the limit doesn't exist at A. So we're out there. Now C, we have a limit that exists at A. The left-hand limit and the right-hand limit agree. They're going to the same spot. However, there's a hole there. F of A is not defined where the graph is headed. And finally, D, again, the limit exists. Left-hand and right-hand limits agree, but where the graph is defined is not at the limit. We have a couple different types of discontinuity. We have what we call a non-removable discontinuity. That could be an infinite discontinuity where the graph just goes off into oblivion somewhere in the middle. Or a jump discontinuity where the limits don't exist. Or we could have a removable discontinuity, and that's some sort of hole in the graph. Now, a hole in the graph is, if you're looking at an equation, something that cancels out. So keep that in mind. We're going to look at this graph, and at each discontinuity, determine whether it's a non-removable or removable discontinuity. So we're just going along the graph here. Everything's happy, but at -8, it is not continuous. Is that removable or non-removable? Well, it's a hole that just got bumped out, so that would be a removable discontinuity. All right, continuing on the graph. Oh, we have a discontinuity right here. Removable or non-removable? That is non-removable because right in the middle here, the graph heads off into its own direction. All right, moving on. Okay, what about this one? That's also a non-removable discontinuity. That's a jump discontinuity. Now we could also talk about open interval limits. Remember in a previous lesson, we were talking about inverses, and I said like the sign has an inverse if you shrink its domain. If you look at the graph of tangent of x, it's clearly not continuous because tangent of x is undefined at any multiple of pi over 2. However, if we shrink it a little bit, we have a continuous graph. Tangent of x is continuous on this open interval from negative pi over 2 to pi over 2. So it has some continuity. We just have to specify where it is. If we re-expand the graph, we could say that tangent of x is continuous on any open interval in its domain. Here's sine of 1 over x. Now, it looks very continuous. However, we have this limitation right here. You can't have 0 on the bottom of a fraction. So sine of 1 over x is undefined at 0. The rest of the time it's fine. So that's basically what we have to say. Sine of 1 over x is continuous on the open intervals negative infinity to 0 and 0 to infinity. Here we have a piecewise function, and it says determine the value or values of a for which the function f of x will be continuous. So at any x less than or equal to 2, our function is defined by this polynomial, ax squared plus 3. Anything greater than 2, we have a different polynomial, x plus 5. Now polynomials themselves, just regular old polynomials, are continuous. But here at 2, we're switching polynomials. So we have to make sure that the polynomials have the same value at 2. All right, so here's what we're going to do. We're going to plug in 2 for our x values and make sure that the polynomial on top is equal to the polynomial on the bottom. So a times 2 squared plus 3, that has to equal 2 plus 5. So we'll just solve for a. 2 plus 5 is 7. If you subtract 3 from that, we've got 4a equals 4. So a equals 1. So as long as a equals 1, this would be a continuous piecewise function. The intermediate value theorem is a big deal. It says if f is continuous on a closed interval ab, and f of a does not equal f of b, meaning wherever it starts, it doesn't end up there, and k is any number between f of a and f of b, then there is at least one number c in ab such that f of c equals k. Oh my gosh, that is so many words. So let me show you graphically what all that just said. So here we have this beautiful graph. It's continuous, and we're saying that it's continuous on this closed interval between a and b. Now, f of a is in a different spot than f of b. That's important. What we're saying is that in between a and b, there's some value, some x value of c, such that f of c is between f of b and f of a. Now let's look at a more specific version. We have another lovely graph here, and it's defined and continuous between a and b. Now what's important is that f of a is greater than 0, and f of b is less than 0. So what we know is somewhere between a and b, there's a c, and if you plug that c into the function, the value of the function has to be 0. So if the graph starts above 0 and ends up below 0, somewhere in between, it has to be 0. Let's practice a little bit. So we're going to apply the intermediate value theorem, if possible, on this interval 0, 5, so that f of c equals 1 for f of x equals x squared minus 1. What does that even mean? Well, first of all, f is continuous over all reals. We know that because this is just a lovely, very pretty polynomial. Next, we need to look at f of 0 and f of 5. So you plug in 0, and f of 0 is negative 1. Plug in 5, f of 5 is 29. And is negative 1 the same thing as 29? It's not. The graph is ending in different spots. Therefore, by the intermediate value theorem, there has to exist a value c where f of c equals 1 between 0 and 5. I mean, basically, if you have negative 1 and you have 29, there's a 1 somewhere between negative 1 and 29. That's what it's saying. You need to make that a prettier one. Whatever. Here's the graph just so you can see it. It's always good if you do some sort of algebraic or analytic problem to, if possible, always look at the graph. Now we're going to show that the function x cubed plus 2x minus 1 has a 0 on the interval negative 1 to 1. Step 1, is this a continuous function? Yes, this is a continuous function, and you need to state that. All polynomials are continuous functions. 2, we're going to have to check out where is the graph at x equals negative 1. It's at negative 4. Okay, that's less than 0. Where is the graph at x equals 1? It's at 2. That's greater than 0. F of negative 1 does not equal f of 1. And is there a 0 somewhere between negative 4 and 2? Yes, there is. So there does exist a value c where f of c equals 0 on negative 1, 1. Sometimes you don't have all the information about a function. You just have what they call selected values. So here we have a table, and it says that a car travels on a straight track. During the time interval 0 to 60 seconds, the car's velocity is measured in feet per second and is a continuous function. That's important. They're telling you it's a continuous function. The table below shows selected values of the function. So for 0 to 60 seconds, must there be a time, t, when v of t equals negative 5? Well, I don't know. Let's look. It goes from negative 20 to negative 30. There's no negative 5 between that. Negative 30 and negative 20, no negative 5 between those. Negative 20, negative 14, no. Negative 14, negative 10, no. Negative 10, 0. Aha! Negative 5 is between negative 10 and 0. So here's how we justify that. V of t is continuous over all reals. V of 35 equals negative 10. V of 50 equals 0. Those are different values. Therefore, between 35 and 50 seconds, there is a time when v of t equals negative 5 because negative 5 is between negative 10 and 0. I think this one's a little tricky. Let g be a continuous function. Okay, take note of that. Selected values of g of x are given in the table below. For which value of k, this is what we're looking for, this should say would the equation g of x equals 3/4 have at least two solutions on the closed interval 2, 8? Okay, let's draw a picture. And what we need to look at is to the left of k and to the right of k, what's going on. Well, somewhere on this graph we have the point 3, 4, and then somewhere on the graph we have the point 5, 5. And then we have the equation g of x equals 3/4 cutting right through it. Okay, now between those is this point 4k, and that's what we're trying to figure out. What could k be? Well, if this is the line 3/4, k has to be something less than 3/4. So not 1, not equal to 3/4, not 1.5. So 9/16. Okay, back to a piecewise function. We love these. Does the intermediate value theorem guarantee a y value k between 5 and 10 such that k is between f of 5 and f of 10? Justify your answer. I don't know. Like, we don't have a lot to go on, but we'll start with, is the graph continuous? Because in order to use the intermediate value theorem, we have to know if the graph is continuous. So we'll just start there. Well, we know between 5 and 10, the graph is continuous because it's always 6. It's just a continuous y equals 6 graph. Okay, but what about at 5? So when it switches functions at 5, what's happening there? If we plug in 5 to the top, we get 5 minus 3 squared. That's 2 squared, which is 4. The limit as x approaches 5 from the right, that's this bottom part, is 6. F of 5 is not equal to that limit, which means the intermediate value theorem doesn't apply. F of x isn't continuous. We don't even do the problem. We just move on. So we'll leave it there for now. Thanks for being here.